Central webcast entitled Enhancing Transmission Capacity and Existing Rights of Way with ACCC Conductor. Now I'm happy to turn the floor over to the moderator of today's event, Mike Beeler, COO of Mike Beeler and Associates. To kick things off, Mike, welcome to the event. You have the floor.
Thank you very much, PJ. It's a pleasure to be here, and thank you everybody for joining us. This is a very hot topic, and I'm really excited to have some great panelists together today for the next 90 minutes. So with us today, each of these guys is going to say hello briefly and just give a quick introduction, but so you can hear their voice and identify them. We will start off with Jim Lehan from NV Energy. Jim, give us a quick greeting, if you would, please.
Yeah, good morning, everybody. It's Jim Lehan, NV Energy, and I'm based out of Reno, Nevada, and I'm glad to be here today. Thanks.
Glad to have you, Jim. Also from Southern Cal Edison is Robin Castro. Robin, quick greeting and maybe a little brief background about yourself.
Yeah, good morning, everyone. Robin Castro here. I am the Asset Engineering Manager for Southern California Edison, responsible for transmission, distribution, overhead conductor, and cable. I'm excited to be here this morning.
Thanks, Robin. We're excited to have you. Dave Bryant. Dave is our subject matter expert today from CTC Global. So, Dave, give us a quick greeting and say hello.
Well, thanks, Mike. Good morning, everyone. Thanks for joining us, and especially thanks to PJ at Energy Central and Robin and Jim Lehan. Appreciate everybody's support. And this should be a really good conversation. Thank you.
Well, and audience, we want it to be a conversation, so feel free to send your questions in as we go, and we're going to keep it light and conversational and very educational and fast moving for you as well. So as we move on to just a quick intro about some of the industry challenges and insights, and I actually like to even call these things opportunities. Right now in our industry, we just saw this past week where 3 Mile Island is now in the process of being repowered. Google has signed a contract with Constellation Energy to repower 3 Mile Island for 800 megawatts of clean carbon-free power. Why have they done that? Why have we pushed back on nuclear so much in this country for decades of time, and now a company like Google is starting to advance nuclear? Oh, we also see that Amazon is doing the same thing. Oh, we see that Google has signed another contract for small modular reactors. What's going on here? Well, the challenge is that these artificial intelligence data centers are driving demand for load to such heights that we cannot get the transmission capacity into the areas where these server farms are going. And we cannot tell a company that it's going to take us 10 to 15 years to route and permit a new transmission line to feed their 500 to 1,000 megawatt load. Yes, 1,000 megawatts. I know that sounds a lot, but in going to some industry meetings here just recently, utilities are very, very challenged by these massive loads by these big companies that have these data centers. So a mega trend in the industry has been, for at least the last decade, in my opinion, more capacity out of existing rights of way. One of the best assets that a utility has is their existing rights of way, their existing property. And how can I get more transmission capacity out of that existing right-of-way? There's several solutions, but one of the best solutions is by enhancing transmission capacity with new advanced conductors, composite core conductors that allow more ampacity through the same cross-sectional area. So we've got some utilities that actually have experience doing that. And they've got a story of how they got to where they're at today and where they're going in the future. And it's going to be a fascinating story to hear about what their plan is for the future. How are they going to meet these massive loads? How, in fact, are they going to get more capacity out of existing rights of way so that we don't defer to other companies that come in and sign deals with the Googles and the Amazons of the world? Okay, so all that said is just a method of introduction to Dave Bryant, who's going to talk to us a little bit about the technology of these advanced conductors and give us a little bit of background on that. And I would encourage you, audience, as you have questions, go ahead and send in your questions. We'll listen to Dave, give a little bit of intro on the technology, and then we'll go right into Jim and to Robin to tell us about what they're doing at NV Energy and Southern Cal Edison. So Dave Bryant, I would say take it away.
Thanks, Mike, and thanks everybody. I just wanted to spend a couple minutes giving you a little bit of background about CTC. We really, I feel like, started the advanced conductor market back in 2003. You may recall there was a major power outage in the eastern United States and parts of Canada, and that led to a growth and understanding of the need to help mitigate sag and increase capacity to help stabilize the grid. We're really proud of the accomplishments that we've made over the last couple of decades, been 22 actual years. But I think and we went from a group of 6 people to over 600 people today. And I think the real reason for our success, besides just the fact that we offered a real good technical solution, was the fact that we had so much support from our customers, our manufacturing partners, trade associations, even adversaries. They've all driven us to raise the bar, and we continue to work hard to do that. So again, we have a lot of experience, and I appreciate you taking a minute to look at some of these numbers. PJ, you can go ahead and move forward. For those of you that are not familiar with the ACCC Conductor, it uses a hybrid carbon and glass fiber core that's about 70% lighter and about 50% stronger than a conventional steel core. And what's also very significant is the coefficient of thermal expansion is about 10 times less than steel. So as a conductor heats up due to electrical resistance and you're pumping a lot of amps down the line, the composite core prevents conductor from sagging excessively. So this, and the fact that it has additional aluminum content without a weight or diameter penalty, allows you to essentially double the capacity of an existing corridor using existing structures, or conversely, use fewer structures at greater spans because of the lower sag and the higher strength, and that can help reduce the upfront capital costs of new lines. And one of the things that's something that we didn't really expect going into this program, 20 plus years ago, was this energy efficiency attribute of this technology. While initially labeled as a high temperature, low sag, you know that high temperatures equate to high I²R losses. But the fact that we can use about 30% more aluminum without a weight or diameter penalty allows us to reduce the electrical resistance that translates into reduced line losses. Reduced line losses is actually a real big deal, because in addition to burning less fuel and producing less emissions, reduced line losses allows you to free up generation capacity that's otherwise wasted. This is something that's been studied by academics and other people, like the SCS Global Service did a pretty substantial research project on this and certified that our statements about efficiency are actually true and very substantial. We estimate that we've saved cumulatively around 30 million metric tons of CO2. And if you look at trying to accomplish that by spending money on electric cars or some other technologies, the bang for the buck that we offer using this type of technology is really, really good. It's a very low investment for a huge output. Thank you. Next slide.
Yeah, well, I'll just say, Dave, that's interesting background. Go back, you say you've been around for 22 years and you started off with 6 people and today you've got 600 people. Go back to those early days when you're brand new technology and you're rolling out and you're coming out and saying, you know what, I can double the capacity in your corridor, and people go, well, really? Show me, prove it. How did that whole process work? Just a brief background on that.
Well, it wasn't easy, but I tell you what, in previous chapters of my life, I was familiar with aerospace applications, automotive, and other transportation things where advanced technologies were pretty sexy. And I got into this conductor startup project, and I thought, well, that's a pretty mundane application. But the reality is, this has been the most enlightening and challenging program of my life, and it's been a real thrill, and I've really enjoyed learning so much from all the people that have supported us and again challenged us. It's been great. Startups are never that easy, but it's so refreshing to see a technology like this come so far so fast. And if you pay attention to what other people are doing, it's noteworthy, especially with the policymakers that are now in California, the new regulation that's inspiring utilities to actually take a look at advanced conductors and other grid enhancing technologies to help find solutions that we can no longer afford to wait a decade to implement. So
yeah, we certainly cannot afford to wait. It's going to be interesting to hear, Jim, from you and Robin about how you guys approached this when somebody first came in and said, "Oh, have you considered doing this?" So when it's your time to speak, we're going to be eager to hear that story as well. So thanks, Dave, for sharing that.
Thank you. So this slide is a little bit windy, but reconductor projects are sort of what has got us into the game. We've also been used for some really long span applications. We did a mile crossing over a river in Africa about 5 years ago. We've done some lake crossings and some other really long span projects over mountain ranges, things like that, in highly corrosive environments where the steel cores typically don't last that long. One thing that's also really neat about this technology is it dissipates vibration on an order of magnitude more effectively than conventional steel core conductors. And part of that is because these smooth trapezoidal strands rubbing up against a smooth single strand core help dissipate vibration very effectively. And so that's an attribute that can be put to use in any of these types of projects. And while reconductor projects were sort of our bread and butter because we can go double the capacity of an existing corridor without having to switch out structures very quickly and very cost effectively, we've also done plenty of rebuild projects when they want to do some sword hardening. A lot of times they'll install steel or fiberglass poles. But we're seeing more and more new line projects, especially in developing countries that are receiving funding from international development banks who are very keen on improving the efficiency of the transmission and also future-proofing. A lot of times in the United States, people are hesitant to leverage advanced technology because it's a little bit more per meter or per foot for the product, but the ability to future-proof the grid and to be able to have capacity when you don't even know that you need it is fantastic. Final thought on this slide is that when you have an integrated grid that has wires crossing over everywhere, if you have a down line, you can reroute structure, you can reroute power around the downed line or around an area that's highly susceptible to like fire situation. So that also helps improve grid reliability. Additionally, when you add a conductor that has more approved efficiency, it reduces stress on adjacent lines. So you get a net benefit that's greater than the sum of the individual component. And that, by the way, is the definition of a composite material. We can move forward. This slide says a lot. This was data gathered by Hydro One at Kinetrix Lab up in Canada about around 2004, 2005. And they took on a 65-meter span or 225-foot span, they installed in series a bunch of different HTLS conductors in line with an ACSR conductor, and they ran 1600 amps through this Drake-sized conductor. And if you think about the fact that a Drake-sized conductor would have been limited to an operating temperature of around 100 degrees, that would correlate to a sag limitation as well for a newly designed line. And while other high temperature low sag conductors are able to operate as high as 250 degrees C, you'll see that a lot of times they will actually exceed their sag limit if they were used for a reconductoring project. An option would be, of course, to install a larger, heavier conductor, but those would also require structural modifications or replacement. And what's also pretty remarkable about this slide is that the ACCC conductor that's sort of depicted at the top in blue, it's hard to see, actually under the same load operated 60, almost 80 degrees C cooler than other HTLS conductors that were tested at that time. So that's a pretty remarkable reflection of the ACCC conductor's resistance to thermal sag and also ability to operate cooler with much lower losses. And even though people are not operating these conductors typically at these high amperages, not all the time, the line losses associated with them, even at lower flows, it adds up pretty quickly. AEP several years ago completed a 240 circuit mile reconductor of a 345 kV line, and even though that line was lightly loaded, they saved 300,000 megawatt hours per year just in line losses. And that equated to 200,000 metric tons of CO2, which is the equivalent of removing 42,000 cars from the road. And that was just two parallel lines. So the ability for this technology to be used to help reach sustainability goals or reliability goals is really remarkable. Thank you. We can move forward.
So if you have a utility that is serious about ESG and trying to improve their performance there, this is a way that they can do it. That's the message I'm hearing on it.
That is true. And I think we'll see shifts in policy that support the investment in these types of modern technologies to help improve grid efficiency. And so policy changes that are underway now are going to be paint a very bright picture for the future of these types of technologies. Good. So there are a couple of options. The one thing that I'd like the audience to understand is that while the strength of the ACCC conductor compared to steel core conductor, even a high strength steel, is quite much more substantially better, but it is more an elastic product. And what that means is that if you take a steel conductor and you add a lot of ice load, it'll be stiffer and it'll deflect less under heavy ice load, but it will also, if you get it up to about 1% strain, it'll actually stay stretched out. It will not rebound. The ACCC type of core is fully elastic, so even though it might stretch more under a heavy ice event, it will return to its original condition, at least in terms of the core. The aluminum strands will have relaxed, the knee point would have been lowered, which will give you even improved thermal sag, but to mitigate or to manage really long spans or really extreme ice loads, we offer options that include a higher modulus, higher strength, less elastic ULS core, as well as the incorporation with either type of core design with aluminum zirconium alloy. That's a high temperature alloy that can operate at temperatures up to 250 degrees C.
That's good to know. Actually, that was one of the questions from the audience about comparisons ACCC versus ACSS. So thanks for covering that and giving us some of the details. I would say to the audience, continue to send your questions in as we go, because we can weave some of them into the conversation here, especially when we're talking about some of the technology here. So thanks.
There are also,
thanks, Dave.
I'll point out the fact we also have over 100 different conductor designs that have been designed specifically to accommodate utilities problems. So if we're facing a particularly different challenge or unique challenge, we can design a conductor solution that accommodates whatever that challenge might be.
And I see your little note down here at the bottom of the slide about PLS CAD. So PLS CAD can accommodate all these different varieties of conductors, I assume?
That's correct. Their library includes ACCC Conductor. So if you use PLS CAD, that's an easy place to gather information. One thing that I have not pointed out on this deck is that we also have a program that you can find on our website called CCP, Conductor Comparison Program. It's got a database of about 600 different conductor types and sizes, and it can be used at no charge for anybody to compare something that's very specific to what they're looking for. It's also a good way to optimize a conductor selection, but it also does a really good job of comparing ampacity, line losses, sag, and other things, so that it helps you refine your designs going in, as you get your project started. Thank you. Next slide. One thing that's unique to the ACCC conductor is the hardware design. There are other composite designs that use conventional or semi-conventional compression hardware. We have found that those can be problematic. So we've designed a collet that actually allows some elastic flex of the core without causing any crushing or damage. We've got about 1 million of these things up in the air, and it's a very simple device to use, very straightforward, and it really only takes a crescent wrench to attach. So it's a very important component. Looking at a system solution, and this is a key component of providing a solution that will give you the reliability you're looking for.
So when you say you've got about 1 million of them up in the air, are you speaking literally or figuratively?
if you counted all the call it assemblies that have been delivered, it would be in the million plus neighborhood. A dead end device is very similar to this. It's just two call it assemblies back to back, and aluminum sleeves are put on top and use a conventional compression die to attach. Very straightforward design. Okay, next slide. I've only got 2 slides left, and so we can move on to hear what Jim and Robin would like to share with us. But one thing that's also been part of our development program that's been going on for a long time is what we call the ACCC InfoCore system. The ACCC InfoCore system uses embedded optical fibers, and the linemen are given devices that are used to cut this and prep it, and then devices that can send a signal and receive a signal that are then transferred to a cloud-based storage thing. What's also, so this device is really designed to check core integrity after an installation, or even before, if there was a impact from a forklift or something happened that was not considered to be normal. This is why. It is important to understand also that, like any other type of conductor, the ACCC conductor has bending limitations, and these are these relate to installation practices and making sure you have the correct sheave wheel. But what can happen is if you have a sheave wheel that's not large enough, or you have the conductor jump off the side of a piece of equipment and the core bends excessively, it can actually cause a buckling failure, which the InfoCore system can identify, even though you may not see any damage to the outer aluminum strands. So this is a great technology. We've deployed, there are 24 projects that were completed between 2020 and 2023, about 4,500 kilometers installed during that time frame when it was initially introduced, and expect nearly 10,000 kilometers to be completed at installations before the end of this year. I'm not sure how many projects we'll hit with the InfoCore off the top of my head, but it's been quite successful and very well received. It also really established a nice foundation for additional technology leveraging. So this is, we're just getting started. You'll see a lot more coming from CTC in the coming months. So stay tuned. And one last slide for me. And this is basically, I wanted to share with you guys kind of a summary of what this technology can do. First of all, I'd like to say that we do our best to make sure that everything that we learn is passed along to people that are interested in technology. We have a lot of experience to share, and we're really pleased that we could have this conversation with you today. But it's reconductoring with advanced conductors can help you, double the capacity of an existing corridor very, very quickly at a far lower cost and construction timeframes than would otherwise be required. Permitting is very fast and generally can be done under a maintenance. So it's a great solution. It's very well proven. We've got 1,325 projects that have been completed in 67 countries. We're proud of that accomplishment, and we're just getting started. So thank you so much. Mike, back to you.
Well, that's fascinating. I got a question from the audience here that's kind of pretty cool, and then we'll use that as we transition to NV Energy. But here's a question from the audience. It says, in Loudoun County, Virginia, we have 181 data centers and growing, the largest concentration in the nation. We're now using 500 kV as distribution lines, kind of in quote, which obviously that's that's in quotes for the data centers. We're shifting to 765 kV. They just put out a press release that they have submitted to PJM a 765 kV solution going into northern Virginia for these data centers. And it would to bring power from hundreds of miles away. Here's the question. Would it make sense to reconductor our existing 500 kV lines to move higher power around the states? We have many corridors with 2 lines that could help with reliability. What do you think about reconductoring 500 kV lines? Dave, is that something that CTC has done before, or is that a viable solution?
we've done everything from 11 kV to 1100 kV and AC and DC. And I think that it definitely would be worth looking into. And I'm certain that assuming that substation, transformers and other equipment could be modified to accommodate, the increase in capacity, I think it'd be criminal not to actually investigate this as an alternative. Conversely, looking at converting a 500 kV to a 765, there might be more flexibility in actually converting it using advanced conductors because of the improved stability. So there's a lot to talk about. We've got a dozen application engineers spread around the world that are also be happy to look at this. If you want to reach out to me, you can get a hold of me through info@ctcglobal.com and be more than happy to connect you with an application engineer that could support you. Thank you.
Great. We have some more questions coming through for you on the technicalities here, but I think we're going to move on to NV Energy and Jim Lehan. Jim, I know you've got a great story to tell of some of the interesting things that you've done over the years and some of the things that you've got planned in the future with this kind of technology. So go ahead and give us a little bit of an introduction to NV Energy and tell us some new things.
Yeah, thank you, Mike. Well, I'm not a CTC salesman, I'm just an engineer, but I'll tell you a little bit about our experience. First, real quick, NV Energy, little overview here. We have 2 major service territories. We are a Berkshire Hathaway company. We serve the vast majority of all the load in the state of Nevada. We have 2 sort of territories down the south. We have Las Vegas, which is got about 1,400 miles of transmission line and from 69 to 525 kV. I've been with NV Energy for 38 years, most of that time in the engineering function, doing transmission design. I am out of the Reno office, and we work on lines all over northern Nevada. We have industrial load. We are also starting to see a lot of data centers coming into our area. And we have a lot of gold mining, a lot of major mines in the state of Nevada, so we have a lot of mining customers. We have about 4,200 miles of transmission line, and that ranges from 60 kV up to 345 kV. I'll go next. Let's see. Sorry, I don't have a button. Okay, I'm just going to talk a little about our experience at NV Energy with ACCC. We started off kind of modest. Our first project was on a 120 kV line you see in the photo here. This was 2009. This line is about 18 miles long. It was originally constructed in 1956. It's just wood pole H-frame. It's 120 kV. It was originally constructed with a 4/0 copper conductor. And in 2009, our transmission planning group said, hey, we need to upgrade this. It's one of the main connections between Reno and Carson City. We need to upgrade this to 954 ACSR, or at least something with 900 amps. Of course, the line was not designed for 954. Most of the structures did not have adequate strength for a wire that much bigger. And we had a PLS CAD model. We just restrung the whole thing with 954, and there was over half the spans didn't have the ground clearance for a 954 conductor. So we were looking at a full tear down and rebuild of this line, which would require all new special use permitting with the city. The problem we had is this line, when constructed in 1956, was way outside of town up in the hills. But by 2009, a lot of this line was surrounded by residential expansion. It even goes through a couple of gated private golf course communities. People built their houses right up next to the right of way. We literally have structures in people's backyards now, which is not ideal, but that's the way that it is. So a new special use permit was probably just no way going to get approved. And we anticipated a lot of this line would probably end up having to go underground. So this is the first time that we looked at an alternative conductor. We looked at ACSS. We have a little bit of ACSS in Las Vegas. We had never used it in northern Nevada. We looked at ACCC, and we looked at a couple other, what do you want to call them, alternative high temperature conductors. There's C7, there's ACCR. We looked at a few of them, did our own evaluation, and We really liked the way a 431 ACCC Lynette conductor worked on this line. It solved 90% of all the problems. We did have to change just a few structures, but we were able to rebuild this line under maintenance. So we avoided all the permitting. We saved most of the original structures. We did a few upgrades here and there, changed out some old cross arms, changed out some anchors to make sure our dead ends were nice and strong. And we did it. And it was our first conductor with our first job with ACCC Conductor, and it was quite a success. Go to the next slide.
So were the people from CTC Global out there with you on a pretty regular basis when you were doing this? This is the very first installation. It was a while back in 2009. So how'd that whole process work?
Yeah, that worked very well. We tried to vet this product as much as we could. I think we were one of the first users of ACCC in the Western US. But we went down to Southern California, took a factory tour. We looked at all their testing information. And CTC was really good about having their master installers, on site for training. There's just some photos here of the line that was under construction. We, our crews are used to using, every crew at that point is used to using steel core conductor, and they just know how to handle it and what to do. And this is a little bit different animal. So we got training with their installers. We had to use different size, shivs, travelers. Had to handle the wire pulling, check your tensions, check your setups, all those kind of things. And we learned how to use different types of clamps, right? We had to get new kinds of hardware that we didn't necessarily stock. And the bottom right there, you can see we normally use bolted clamps. These are armor grip suspension clamps. So a little bit different hardware, a little bit different handling, but it all worked out really well. It was a learning experience. But it worked well. We thought, got it all done. I thought, hey, this was a good success. So next slide.
So you started off by saying you're a Berkshire Hathaway company. Have other companies within Berkshire Hathaway picked up on this as well with you? Do you guys talk like that amongst companies at Berkshire Hathaway?
Well, you'd think we would, but we're a little more siloed. Everybody's so busy, and all of our service territories are so different. Even in our own company, Reno and Las Vegas have completely different loading conditions.
Yeah.
Las Vegas has high winds and they're an NESC light loading area. We have more ice storms in the north. We're NESC medium and heavy. A lot of our sister companies are like in Portland and Utah. So unfortunately, I'm not sure how many of these type of projects or high temperature conductors they've used, but I know everybody's looking at it. So 2010, we had another project come up very similar, another 120 kV line, 14 miles long. This one was built in 1965, wood pole H-frames and 636 ACSR conductor. What you see in the photo there, a short segment of this line was actually modified in the 1980s, and it was double circuit with a 345 kV line on pretty big self-supporting steel poles. The line required upgrade to 1200 amps. And again, the old wood H-frames were not going to support the size conductor we needed. And we would have to be back with the city again doing a full rebuild. And this conductor, although it was on a different side of town, was also surrounded by new homes, new subdivisions, and it went right through a nice golf course. And we were not looking forward to trying to re-permit that in its existing location. So we took a look at 1026 ACCC Drake conductor. Again, it's nice having a PLS CAD model. You just go in and change the conductor, and there it is, and go through and analyze everything. It was, again, a very good solution. We didn't have to modify the steel poles on the 345 double circuit at all. They just worked just fine. The wood H-frames, they only had to change out a few of them. And we got a second project done with ACCC in a different size. And again, it just turned out to be very successful.
So, Jim, a couple questions are coming in from the audience around how does the conductor respond after it's installed? So you've designed it, you've installed it, now you're going to operate and maintain it. What are the characteristics with regard to creep? Another question was, what about galloping? Does it gallop the same way the traditional conductors that you guys used gallop. If in fact even galloping is an issue for you, it might be up in the Reno area. Any comments about that?
Yeah, galloping, Dave Bryant might be able to answer this better than myself, but
Yeah, I was going to say,
when
David, you
we
might want to weigh in on this as well.
when we do the design, we treat it like any other conductor and check for galloping, right? So we make sure we're maintaining the proper phase spacing and looking for galloping. Now, does it behave exactly the same? I can't say. Does it shed ice? Maybe easier than an ACSR, maybe, but we just assume it's like any other conductor and we check for galloping, conditions. Creep, Dave, you can answer this better than myself, but creep is not a big issue with ACCC conductor. You want to elaborate, Dave, at all?
Sure. Yeah, the core is impervious from creep. Creep just doesn't occur with the core. And when you're doing an analysis of PLS CAD, you can check the box so that the creep is not a concern. What will happen after a heavy ice load, the aluminum strands will elongate and they will become more relaxed on the conductor, which not only lowers the thermal knee point, it also improves resistance or improves vibration performance. And
Thank you for that.
We can go through our application engineering team and be very, very specific.
Okay. That's a good question. How about the next slide? Okay. So we had one new line in 2009 and one new line in 2010. And one of the interesting things when you're working with transmission linemen and you give them this new product, they look at it, oh, what is this stuff? What's this plastic core? Anything that's not metal, they think it's plastic, right? And they're like, oh, this stuff's not going to work. It's not strong. This is terrible. Well, 2010, we had a massive windstorm blow through Reno. My sympathies to anybody living in the hurricane zones. We don't have hurricanes in Reno, but we can get 80, 90 mile an hour windstorms blow through. And we had a really bad one in 2010, damaged a lot of lines. The photo you see there on the top right is actual the 107 line that we reconducted with 431 ACCC. We had a number of structures try to rip up out of the ground. And we got in there and we fixed it and inspected everything. And there was no damage to the conductor, fortunately. In 2012, and if you live in the West, you might understand this, we had a major wildfire burn through a section of land south of Reno and went right through the 107 line. We had 5 structures destroyed. It's hard to see in the photo, but in the foreground there's an H-frame laying on the ground, or what's left of it. A couple of these structures were so bad, we went to look at them, all there was a metal cross arm and some porcelain. There was no wood left. Everything was gone. And I remember when I saw that on the news, I thought, oh no, we just put up this new wire. We burned it down. I'm going to have to go out there and scramble to get some 954 to replace this because we didn't have ACCC, a lot on hand at the time, and this was an emergency. Well, we went out, did a thorough inspection, looked very closely at the connection points and the wire, didn't see any major damage. So, and being an emergency, we rebuilt the line and put that wire right back in the air. I couldn't tell you that there was no damage to the core, but there was no damage to the aluminum, and the core didn't break. We didn't, try to cut out a piece and send it for lab testing or anything like that. It was an emergency. We rebuilt it. We put it back in the air, and it's been standing strong ever since with no issues. So we've done our own little, non-destructive testing, if you will, on ACCC, and this kind of convinced us. Our crews were out there putting this stuff back in the air going, wow, well, look at this stuff. It's pretty tough. And honestly, both of these lines, this is 431 ACCC. It's one of the smallest cores you can get. So if anything's, going to break, it would be this one. But it had no damage. Also, the 105, the other line that we reconducted during that windstorm, I don't have a picture here, but we actually had an H-frame blow right up out of the ground. And it hit the ground and came crashing down, and we replaced it and put it right back in the air as well. So
here's a question from the audience for you, Jim, right along the lines of what you're talking about. Did your crews get more comfortable with ACCC, after they installed it a few times? It sounds like maybe they did.
Yes, absolutely. You have to experience it. You have to get your hands on it, test it. One of the things that's always kind of fun, if you get a new guy who goes, look, you show him the core, he's like, I could break that. Say, okay. So we get a little piece of, about a 3-foot piece of wire, pull the aluminum off and give them a piece of core and go, here, break it, go for it. And I tell you what, you can take that stuff, even the small core, bend it over your knee as hard as you can. I cannot get a lineman to possibly break this stuff. It is absolutely super, super, super strong, especially in bending. Now you can break this core in shear. That was one of our learning experiences on our first job. We had, they were putting the collet and housing together. They got the collet and the housing right put together. And at that one moment, you have a piece of core coming out of the collet, and there's a 90-degree sharp stainless steel piece of hardware. And they had the crimping tool and hung the crimping tool about 3 feet out on the wire and broke the core. It's about the only way you can possibly break this stuff is in shear and a very sharp, like, you know, putting it in a vise or on the edge of a stainless steel core and bending it. In bending, you just cannot damage this core in any kind of traveler. The reason for the larger travelers when you're installing this is not just protect the core, it's to protect the aluminum. And this is true with any annealed aluminum high temperature conductor. It's very soft. And if your travelers are too small, you'll start deforming the wire and eventually you birdcage the wire. We've done that a couple times, and again, it was installation error. But yeah, the core is extremely strong. So next. Next slide. There we go. 2015, this is when load growth started to go crazy in the Reno area.
And by the way, that was the next question.
Tesla built their gigafactory at the Tahoe Reno Industrial Center. It's about 15 miles east of Reno. They initially came in, you know, with some big plans, and they needed very large amount of power. We were looking at 120 kV. That's the service that they wanted to take. We were looking at a bundled 1272 conductor. Well, we don't really have any bundled conductor standards for 120 kV. And we decided, why don't we take a look at a really big ACCC conductor, a 1949 ACCC lapwing. It has, I think it's good for over 2,500 amps, and it was going to do the job. So this was our first job with new construction, not a reconductor. We built this about 2 miles of line with 1949 ACCC lapwing to the Tesla Gigafactory, and it worked out great. I think next slide. What else do I have?
So there was no pushback at the company when you said, hey, we want to use this new conductor to go serve Tesla?
No, you know, a lot of times conductor is chosen by transmission planning. They say, okay, we need this many amps. Here's the formula. We go pick this wire. And of course, we're not just picking wires at random. We have different size wires in stock in our inventory, right? We have 397, 795, 954. And I'll just roll right into this slide. After Tesla came into this area, we started seeing rapid growth of data centers. It's the same story that's being told around the country. We now have Apple, Google, Switch, and about 4 more east of Reno. They are, as you mentioned earlier, they are requesting massive amounts of power, just off the charts. We initially built a 120 kV loop. It's about 15 miles long, all the way around the Tahoe Reno Industrial Center. There's all kinds of industrial work, buildings and companies out there. And it's a loop of 1949 ACCC. It's good to feed almost everything. And the photo at right I actually took last week. This is a photo of a quad circuit structure coming out of a new switching station going to serve 2 data centers and a biofuel plant. So we have, since then, we have standardized on 431, 1026, and 1949 ACCC conductors. They are now a stock item in our inventory. We have 20 individual circuits with ACCC conductor in our system. A lot of them are short. They're 1 mile, 2 mile, 5 miles, but we have over 76 miles in service. We have 5 more projects currently in construction right now, or just about through permitting for another 52 miles. And we have more on the way. I need to update this slide. There's probably 3 more to do. And as I said, it's all a stock item for us now. So we just pull it from stock. We stock the hardware, we stock the wire. It's just become a standard for us because it is so high capacity, and we never had this problem before where suddenly you need enormous amounts of power on relatively low voltage, 120 kV transmission lines. But with all the growth out there, we are putting 1949 up everywhere we can. And that's where we're at. We have not used it yet at any higher voltages, but we do have a plan right now for a 345 transmission line. Well, we're bringing technically 345 transmission lines into this industrial area to serve these data centers. And some of those are probably going to be using ACCC Conductor as well. So next slide. Okay, I think this is my last slide. Just a couple of comments on lessons learned. The first one's on T-taps. We've had, where these lines drop down into substations, we've had some bird caging issues. If you're trying to tap the wire out from the A-frame or dead end, you don't leave a lot of wire between the compression dead end and that T-tap. We fixed that by going to a smaller, like a swage type T-tap. We were over compressing T-taps. They're not a structural component. They're not compressing the core for tension. It's just an electrical connection, and we were overdoing it. So we still have to remember this is high temperature wire. It's annealed aluminum. It's very soft, so you don't want to compress it too much, or you have to give that wire someplace to go when you do. Also, ACCC has a very high strength core. You can't just string it at normal tensions you would for like an ACSR, which is kind of handy. You can actually design lines now for sag. Say, well, let's see, I've got a 400-foot span. I think I only want about 4 feet of sag. A lot of our single pole construction has distribution underbuild, so you watch your sag, and then you pick a tension to match, and you don't have to worry about a lot more sag. The wire just doesn't move much, whether it's hot or cold or super high temperature. So you can customize your wire stringing tensions. Another point, ACCC Conductor is lightweight. It's a lot lighter than an ACSR. If you're reconductoring an H-frame or any kind of structure with suspension insulators, and you're just going to change out wire for wire, you have to pay close attention to your insulator swing. ACCC is lightweight. It will blow out farther than an ACSR, at the same sag. So you need to check your insulator swing over. That can be a little surprise. Training, of course, CTC is always there for training. Any new contractor that we bring on board or any new lineman that's going to be working on it, we bring CTC in and make sure everybody gets training, because again, there's certain ways to handle annealed aluminum wire, and they're very good about making sure we do it right. And last point there, I just made a note. With 1949 conductor and good for over 2,500 amps, we had to go back to the substations and go, oh, wait a minute, we only have 2,000 amp switches and 2,000 amp bus. So it's a great way to increase capacity on your lines. You got to be prepared to increase your substations as well.
There you go.
That's about all I have from NV Energy.
That is a great overview. We really appreciate it. So one of my takeaways was that since about 2015 to present, you guys you've got the conductor and all of the components that go with it in stock. You're training your new line crews and your contractors that come on property with the technology of how to install it. It sounds like some of these brand new projects that are feeding these data centers, you mentioned 345 kV lines for data centers, are likely going to go with composite core conductors. That's pretty exciting.
Yeah, we have an immense amount of work right now. The growth of these data centers drives other growth in the area. We're buried with work.
Yeah, well, appreciate that. And as we get ready to transition to Southern Cal Edison here, Robin Castro, thank you very much, Jim, for that background at NV Energy, and appreciate all the things that you guys have been doing there. And
my pleasure.
sharing,
I'm glad I could share.
yeah, and sharing that with the industry. I think the industry really is better when we're able to share things like that. And I know sometimes we compete for some of these opportunities. You had to compete to get Tesla, obviously. And so, and everybody's competing for data centers. So as we move to Southern Cal Edison, where they're reimagining the grid, Robin, you've got some great things going on there. Again, You've got serious load growth. You have some huge initiatives for electrification. We've heard your CEO stand up and talk about it when he led EEI, about the electrification of everything. Your governor has got a mandate by 2035 for no more internal combustion engines, which is a great opportunity for electric vehicles. And all of that requires electricity. So you guys are expanding the grid. Tell us a little bit about Southern Cal Edison, a little bit maybe more about your role and some of the cool things you're doing at Edison.
Yeah, appreciate that. First of all, before I continue, I want to say, Jim, great presentation. Thank you for all the information you shared. But yeah, my team is responsible for mission conductor. So we are in the midst of looking for new technology, right? And looking to pilot anything that could help us meet future demand. So in the next few slides, I will be going over some of our background, discuss some of our challenges and drivers for projects, our experience with ACCC, also go over some of our lessons learned from design and construction, and lastly, talk about our current state of advanced conductors and also what our future outlook will be based on upcoming transmission needs. So on this slide here, our territory is fairly large, 50,000 square mile service territory, which includes 15 counties in our service area. Over 5 million customer accounts are served by SCE. Our network of transmission assets includes over 1,100 transmission circuits ranging from 66 kV to 500 kV, with over 13,000 miles of transmission lines. We do have a good amount of ACCC conductor installed, so about 385 circuit miles, a little bit on 66, more on 115 kV, and the bulk of it is at 230 kV. We are expecting by 2045 a 40% increase in peak load, and I'll talk about what those drivers are in the next slide, I believe. But we're also forecasting 80 gigawatts of new clean generation, which includes wind and solar, and also approximately 30 gigawatts of battery storage to be able to meet those, that 40% increase in peak load. We can move forward to the next slide, please.
So you've already got 385 circuit miles installed. That's quite a bit. Have you been doing this for how many years, do you think?
Yeah, so we started, I believe, in 2017.
Okay.
Using ACCC, so we have, almost 10 years of experience.
Yeah, good, thank you.
All right, so on this slide, as many utilities, we have some similar challenges. One of them is, existing aging infrastructure that cannot accommodate large conductors. So I'll go over a few examples where we've had structures that are 56 years old. And there's other areas that are, we have structures that are 80 to 100 years old. So that makes it challenging when we need to reconductor to a larger conductor to get more capacity. In California, as a lot of people know, environmental is a big concern or a big issue. So permitting and licensing to build a new line can take a very long time, sometimes over 10 years. So that's a big challenge. Also, because some of our territory is in highly developed areas, metro areas, that also limits how much right away we can obtain, and therefore we're limited on how many lines we can build. And lastly, limited resources, right? We only have so many engineers, so many contractors, not only internal but externally, to be able to design, build, and execute what we see forthcoming in the future. Moving on to project drivers, I think we haven't seen too many data centers in our area like Jim has in Nevada Energy. But there's a lot of future local loading, such as building electrification, transportation electrification, and also a big reduction in carbon footprint, which, my CEO and other other executives have talked about in different committees and seminars. In addition, we will need a lot of, there's going to be a lot of clean generation coming into our service territory and storage. And in addition to that, we're also going to need to import energy from other states. So a lot of different drivers that will require us to build new lines and also reconductor existing lines to meet some of the current goals by the state. All right, next slide, please. All right, I wanted to break it up a little bit and just show a couple of pictures on some of our helicopter work that we've done using ACCC. For this particular project, some of the structures needed to be completely removed, and all conductor needed to be completely removed as well. And therefore, we needed to put in pull in new hardline using helicopter work to be able to install the new conductor. In this particular scenario, ACCC was used for the design to meet ampacity requirements, meet the clearances requirements, and also minimize high structures. All right, next slide, please. All right. So I'm going to be going over two specific projects. I know we've been using ACCC since 2017, 2018, and those first initial projects were relatively smaller. This one here is a project in the Lake Success area that was completed in 2022. It involved two circuits going through a lake reservoir. So if you can see the picture on the bottom left, those are the two single circuit towers at 230 kV. The picture on the left is showing, when during the summer when you have snow melt, how high the water can get. An interesting fact is that because it is a reservoir, sailing boats are allowed there. So if you could, when we're thinking about some of the clearance issues, we had to take into account the possibility that a sailing boat with the mast can be under our line. So that was an interesting, item to take into account for the design. As I stated before, it's the project involves 4 total circuit miles. So because this is a 2 circuits, it was 2 miles per circuit. One of the lines was built in the 1920s, and the other one was built in the 1950s. The line that was built in the 1920s had existing 1033 ACSR curlew. The 1950 line had 605 kcmil ACSR, so teal conductor. In the 1960s, there was a dam built, and due to a recent proposed dam modifications, existing conductor clearances at that time were not adequate due to the new water levels that the dam modifications would result in. And so, in order to minimize the scope for the project, 713 kcmil ACCC dub was used to minimize the number of structures to be replaced, and also minimize the height as well due to the sag. We did have some interesting choices in design for the H-frame structures, because we needed to take into account the possible rise in water, and therefore we used hybrid poles. The hybrid poles had a concrete base to account for the changing water levels, and also used a flange joint for the steel structures that were above the concrete base. So again, ACCC did work here very well to minimize the sag, and also limit the number of structures that needed to be replaced.
Robin, let me ask you a question here. So you've got a couple of very unique examples here. You're getting ready to tell us about this next one with InfoCore. Do your engineers have a general understanding, and your consultants as well, that this technology is available, and then they're looking for these unique applications where it fits perfectly, where it's, hey, I can't touch this line, it was built in the 20s? and I need to do something special and unique, and let me look at this advanced conductor. Is that coming out of engineering, or is that coming out of planning, or a little bit of both, or how's that work at Edison?
Yeah, so typically engineering provides a list of options, right? We develop a list of options we call our tool chest. And so in the past, obviously, we've used ACSR, ACSS, and now we've introduced ACCC as another tool in our chest for planners to look at in regards to meeting ampacity needs, right? But then our engineering team looks at, okay, the ampacity needs can be met using ACSR, ACSS, or ACCC, but then we really dig a little deeper and look at, you know, maybe span lengths and structure heights and some of the limitations or challenges that we have to deal with depending on project specific requirements.
And so are you able to keep your young engineers apprised of this technology so they know it's an option in the tool chest?
Yeah, so we have developed specifications outlining some of the options in regarding advanced conductors, and ACCC is one of them.
Okay, good, thank you.
All right, if there's no other questions, next slide, please. All right, so on this slide, I'm going to talk about our first use of ACCC Conductor with InfoCore. The LMB project is a 230 kV reconductoring project. We started construction earlier this year. We did a couple of spans out of the substation. You can kind of see that on the bottom left picture. And because of when we started, we had to stop work due to summer peak coming, and we needed the availability of that line. But work has restarted in the last couple of weeks, and we are expecting to complete the work by early next year. The lattice structures were originally installed in the 1960s. The existing conductor is bundle 1033 ACSR core loop. When engineering did the analysis to look at what conductor to use, obviously we looked at ACSR conductor, going to a larger conductor. And the analysis revealed that 50% of the structures will need to be replaced. The analysis also revealed that the towers could not handle 1590 ACSR lapwing. So if we went with something smaller in between, 1033 or 1590, it wouldn't give us the capacity that we needed. We also looked at another product in our tool chest, right, which is a larger ACSS conductor. But using that type of conductor will require 10 to 15 tower replacements, right, which would add scope, which would add time, installation costs, and so forth. So when we looked at ACCC, we were able to recommend to reconductor the 5 circuit miles with 1300 Fort Worth with InfoCore. And what that did for us is, number one, it increased the normal emergency rating by almost 40%. And number two, we didn't need to replace any structure. So for us, that was a big win in regards to schedule. That was a big win in regards to environmental impact, and also obviously cost.
Robin, we had a question way back when Dave was talking about InfoCore. Are you able to access, once the conductor's installed, are you able to access the fiber optics?
Yeah, so I mean, I would defer to Dave because I know the InfoCore technology has gone through multiple iterations of improving the technology, and also being able to dead end with InfoCore, and actually to verify after dead ending as well. So Dave, I don't know if you want to add anything there.
Yeah, Dave, do you want to comment on that?
Sure, you just nailed it. It's as this technology evolves, we've been able to, now we can go back after the installation is taking place, maybe even a decade from now, if there's some type of event, and monitor or inspect the core from the dead end to the splice, and from the splice back to another splice or dead end. So it's the technology has evolved well, and again, like I mentioned, we're just kind of getting started.
Good. Okay, thank you, Dave. Okay, any other comments, Robin, on this particular project?
No, so far you know, we haven't had any issues with, you know, stringing the conductor. We've verified integrity of the core before and after installation. So so far so good.
So Jim said at NV Energy that they're starting to standardize this. They're starting to use it on new construction. They are stocking cable and components, and they're training new linemen and new line crews and contractors. Have you got that far at Edison yet, or how far along that learning curve are you?
Yeah, so no, we definitely recommend training anytime a new contractor or a new crew, because our territory is so big, right? We may not have the same crews working on this conductor constantly, right? So anytime we are going to install or reconductor a line or build a new line, we would have CTC come out and provide a couple of master installers to train our folks and make sure that we're all familiar with the you know, the limitations of it. And yeah, in regards to our inventory stock, we do have some stock for emergencies, you know, restoration in case we did have an emergency, but that's part of our normal operating procedure.
Right. I have a question here, and I'm going to kind of throw it open to all three of you. And I appreciate the audience questions coming in, and we're getting ready to have Robin's concluding remarks here. But go ahead and send your questions in. But here's a question about cost. And so I think I'm going to ask Robin and then Jim and then Dave to comment on this. I think I know the answer to this already. Is there a conductor cost per mile comparison of similar current carrying cable of steel tension member versus an ACCC? And so on a pure cost basis, there might be a cost differential. But I think what you guys are describing is that there's so much more than the initial capital cost or cost of the conductor and the components, because you're being able to do so much more with it. That's kind of what I'm hearing. But comment on cost and the way you guys evaluate cost. Let's say we'll start with you, Robin, at Edison, and then we'll go to NV Energy, and then maybe Dave, you can put a bow on it.
Yeah, so when we look at cost, obviously material is one part of the equation, right? We look at how much the conductor is going to cost. We also look at the structure itself, right? How much, if we use this conductor, will that have any impact on the structure? And then we look at, if there is impact, how much cost is that going to require? So we have used, you know, we are using a vendor to raise towers where we need it, but also depending on what conductor you use, you can raise the tower, you know, 10 feet, 20 feet, 30 feet to meet clearances, right? So and that also has some cost associated with raising the tower. There's instances where we need to completely replace a tower, and that will be significant cost because then we got to get permitting involved for staging areas and so forth to be able to reconstruct. And so and in addition to that, the schedule impact, right? So we have a lot of environmental and other regulated agencies that we need to abide and meet the requirements. And so, yes, there might be a cost difference in conductor, but when we look at the total project cost, we think that is minor enough that we proceed with using advanced conductor, in this case, ACCC.
So here, a question just came in, Robin, for you. Have you combined the use of ACCC and tower raising together, or tower raising or reinforcing?
We have, yes. So in areas where, for example, maybe we needed to go 20 feet using a steel core conductor, maybe using ACCC, you only need to raise that tower 10 feet, right? And so there's a cost savings there. So we have used both.
Great. Good. Thank you. Jim, you want to comment about cost, just in general, the energy and how you guys have come to some of your cost conclusions?
Sure. I think Robin kind of hit it on the head. There's so much more involved than just the cost of the wire. We don't have it like a rule of thumb. This is, 10% more or 20% more. It's very project specific, and it's based on what desired outcome you need for that line. Are we doing a reconductor? Is this going to result in permitting, re-permitting, tearing down the line, potential underground. Is it a new line? Do I need bundled conductor versus a single ACCC? There's so many things to consider that you just have to do project by project and look at all of the other costs, far and above just the wire itself.
Yeah, I think our industry needs to do a better job in general of looking at the total cost of ownership of assets, of T&D assets. And I think this next generation of 21st century planners and engineers, and I even sometimes throw data scientists in there as well, are starting to understand that we're just not looking at capital costs. We have to look at what is the O&M over life of the asset. And in this particular case, what's my cost of permitting? Of course, that's an intangible that nobody can really put a dollar value on. But if it takes you 10 years of fighting your community to upgrade a transmission line, okay, you've burned 10 years, and also it's cost you some goodwill as well. So anyway, I won't get going on that high horse. Dave Bryant, what do you think about cost? Give us some comments from your years of perspective.
Yeah, it's typically after the utilities and the engineers do their due diligence, it's always about the cost. So, probably 95% of the projects that we've done under reconductoring have generally saved the utility money and or accommodated a little bit of projected growth. Usually the efficiency aspects are not taken into consideration in the US because those cost of losses are just passed along to consumers. Developing countries, they actually consider that as part of the big picture. But there's one interesting project that one of my associates brought to my attention this morning, and that's a project that it's underway up in Canada by Altalink. It's a 135-kilometer, 240 kV double circuit, double bundled project where they initially designed it for ACSR. They decided to install ACSS Hawk-sized conductor, which is small to medium, and they were able to get a 65% increase in capacity at a cost delta of only about 1%. So the conductor as a component of overall project cost is relatively small, but to get 65% more capacity at a 1% overall cost delta, that's a pretty remarkable story.
Well, it's a remarkable story, and it's for a future that is unidentified, except we know that utilities load is growing tremendously. I was at an event the last couple of weeks where Encore said that they are going to double the size of their load by 2030. So in 5.5 years, they're going to double the size of their load in the metro area that's growing. It's growing with electrification and electric fleets, and it's growing with data centers and crypto miners. And so that's tremendous. And so if you can buy yourself a little extra insurance by putting in a higher capacity conductor at no extra structural cost, it seems like it starts to make more and more sense. And all of a sudden you get down the road and you realize that it did. And I think I'll go back and just comment, Jim Lehan, I think that's what you guys discovered with the rapid growth that you had in the Las Vegas and Reno areas, that made a lot of sense for you guys. If you want to comment on that just real briefly, Jim.
Yeah, well, with the size of these data centers, they come in and they want a lot of power and they want it as fast as we can possibly build it. Some of the small to medium data centers we're hooking up with 120 kV because that's the voltage of the transmission network where they're located. They need so many amps that a high capacity wire like a 1949 ACCC will do the job, as opposed to multiple lines, bundled conductors, or going up to a 230 or a 345 kV. Of course, that only works to a certain extent. We're getting gigawatt data centers, and we're going to have to bring in 345, and we're even looking at 525 kV. We have a 525 kV project in Nevada right now, from Las Vegas to Central Nevada, and we're going to be extending that line up into this area for these data centers. So the growth.
Yeah, that's fascinating. That's fascinating. Good for you. Okay, Robin, we're going to get back to you, and you got a couple slides here to wrap up on with some lessons learned. And I will say there's a question from the audience that I think is perfect for you. It talks about foundations on these structures that you're modifying. So you're adding this conductor, you're going into older structures, maybe you're jacking the structures up or not. But the question from the audience was, what are you doing about foundation analysis and or integrity tests, just to even determine if the original foundation needed any kind of structural integrity left to it. What do you guys do at Edison with that?
Yeah, so we have a group in transmission engineering that specializes in structures. So they deal with looking at foundations, taking soil samples, looking at the steel to see if how much pitting or any corrosion or anything that may impact the structure moving forward. So if we do need to mitigate any of those items, we do include that as part of the project.
Good. Thank you. Okay. Well, so what do you got here for some lessons learned for us?
Yeah, so I think Jim covered it a little bit about, that there are some limitations, limitations in regards to pulling angles and even bending radius that the CTC provides. But there are, and sometimes that also depends on how the pulling plans are designed, right, for specific scenarios, specific rolling spans and whatnot, and also on terrain. So although those are some challenges, there is some important guidelines or mitigation options that CTC provides in their guidebook. And so, if you do get maybe stuck on I'm not being able to meet a certain angle or pulling radius or whatnot, CTC does provide that support. So yeah, one thing that we did learn on this recent construction on the last project that I talked about for the LMB project out of the sub, is that because it is a bundle construction, that the crews were thinking two ways. One was to pull each conductor at a time, or the second option was to pull them both in together. And we actually did both. And at the end, what the crews felt like worked better in regards to eliminating the creep was to pull them both together at the same time. So moving forward, and ultimately it's a matter of preference for the contractor and how they want to do it. But that's one of the lessons learned, is if you pull them together at the same time, you eliminate that potential difference in creep.
Yeah, that sounds like a great idea. Dave, Bryant, you want to comment on that? That sounds like a pretty good lesson.
Yeah, when you initially pull in a conductor, you do get strand settling and a little bit of aluminum creep. So if you want the thermal knee points to be identical, that's a good lesson, a good technique. Pull them both in at the same time.
Thank you for sharing that, Robin. Okay, other thoughts?
Yeah, and another item, and I think there was one more item on that lessons learned slide, and I think Dave hit on it earlier, was regarding ice conditions. So originally, we have obviously areas in mountainous regions, Bishop, Big Bear, and so forth, where we need to use, we have used or designed for ACCC in some of our structures. We did realize that, that typically when you look at ACSR, you typically use the maximum operating temperature because it tends to expand, right? The ice conditions affects it, but not like the maximum operating temperature. For non-ACSR ACCC conductor or ULS ACCC conductor, we did notice that the ice loading conditions made the sag actually more than what we would see at max operating temperature. So for us, that was a key lessons learned for engineers to ensure that, hey, if we are going to be in heavy loading areas, that we are using the appropriate conductor.
Interesting. Good. Okay, what do you got for your future outlook, Robin?
Next slide, please. All right, so currently, since 2016-17, we've installed over 20 projects. I think I mentioned earlier in the previous slide, we have over 380 miles of ACCC conductor installed. We did start with the first generation of ACCC conductor, but recently we have moved to ACCC InfoCore as our standard moving forward. For our future outlook, by 2030, we expect to reconductor 300 to 400 circuit miles, based on what we see the need is for upcoming load growth. And from 2030 to 2045, we are expecting a grid investment of up to 75 billion, which we see as a requirement to be able to integrate bulk renewable generation, and also battery storage, and the increase in being able to serve the load growth. This will include both reconductoring existing lines and also building new circuits. This is my last slide, and if you want additional information as to how we are forecasting the increase loading and some of the investment that we need to make, you can Google SCE Pathway 2045 if you want more information there. So I appreciate everyone's time. Thank you.
Oh, I appreciate that as well, Robin. That's a great background. SCE Pathway 2045 is something that we should definitely check out. $75 billion in grid investment from 2030 to 2045 is very exciting. So we're going to take a few questions here. Keep them coming. We have a little bit of time left, not much actually. We had some questions from the audience, Dave Bryant, that talked a little bit about some of the international work. And I think you said in your opening remarks that you're in 67 countries, I believe. Yeah, 67 countries, 1,325 different projects. Tell us about a couple maybe projects internationally that really stick in your mind that are important.
That's a tough one. We've done projects ranging from mountain crossings, including like crossing the Great Wall of China, down to crossing rivers in the Amazon, linking renewable generation assets. There's some amazing projects that are going on in Europe right now that are susceptible to extreme spans and heavy ice loads. National Grid UK is working on some projects. TenneT is doing a lot of stuff with advanced conductors. Elia in Belgium is rocking and rolling with this technology and using InfoCore. I mean, they're just, I think today we probably have 90, I think last time I get a bi-weekly update, we have 95 active projects going on currently as we speak. And every one of them makes a fantastic case study. So we're greatly appreciative of that. And I think I mentioned briefly in Asian Development Bank has been funding, and other international development banks have been funding projects in places like Bangladesh, Nepal, India, where they're not only interested in supporting economic development by introducing electricity, hopefully clean electricity, but they're also highly motivated by the efficiency aspects of the ACCC conductor to reduce line losses that help environmental objectives, as well as deliver more power at lower cost with cleaner energy and fewer generation assets. So it's working well in a lot of places in the world, including the U.S.
So we got time for one more question from the audience, and I appreciate that international look. And I'm going to come right back to you, Dave, and then we'll come to you, Robin and Jim, for some concluding remarks. But Dave, one last technical question that as I scanned back through the questions, people were asking about galloping. And I know that Jim referenced that a little bit. It wasn't necessarily applicable to his loading characteristics. What do you think about galloping, and how does composite core conductor handle galloping?
Well, the core itself is very tough, but the environmental conditions can cause galloping due to ice shedding or steady winds. We did have a galloping event down in Kingman, Kansas. This is going back 10 plus years ago, where they used class 1 wood poles, and the galloping was so severe it snapped cross arms, but it didn't damage the conductor, and they were able to put the line back in service very quickly. There are also devices that can be added to ACCC conductor to help mitigate galloping or the frequency or the severity. And we have a book that we wrote back in 2012, I believe, that was it has a chapter on galloping and ACCC conductor, and you can find that on our website.
Yeah, and for more information, they can get you at info@ctcglobal.com on that if they want more technical information.
Absolutely. Thank you.
Great. Okay. So Robin, give us some concluding remarks about your thoughts about ACCC Conductor and the great future that you guys have at Southern Cal Edison.
Yeah. Yeah, so I mean, obviously we have a lot of upcoming work in the next 20 years, right? That has been forecasted, and so we're always looking for new ways, new processes, new technology to help us meet our goals. And we feel like advanced conductors is definitely a tool that will help us meet not only our capacity needs, but also our schedule needs based on the amount of work that we have upcoming. So again, very, very excited with how far some of these advanced conductors have come, especially ACCC, and looking forward to making the product better, not only for NV Energy or SAE, but for the utility industry wide.
Yeah, well said. Robin Castro at Southern Cal Edison, thank you so much for joining us today. We really appreciate it. And we appreciate the stories and the lessons learned in particular that you've shared with us today from Southern Cal Edison. So thank you, Robin. Jim Lehan at NV Energy, you have a great story to tell. You have been using this conductor extensively for a long time. You're going to do it on some new construction here in the future. Lots of exciting case studies. Give us a couple of concluding remarks, if you will, please, Jim.
Sure, and thanks again for having me today. I'm always interested in talking about this stuff. Well, hey, we're in the same boat as a lot of other people in the country. We started off, you need a small reconductor here or there, and this is a great option, but we're now getting flooded with so much huge demand, not only from the data centers, but all of these data centers, they want to be green, right? So we have all kinds of applications from renewable energy providers too, solar, wind, geothermal, a lot of geothermal in Nevada. So it's almost every day our transmission planning department is looking at more interconnection requests, more load requests, and reconductoring or building up front with large high capacity conductor is not really a strange thing anymore. It's becoming more and more mainstream on almost every project that we look at. So we have very good experience with ACCC Conductor. We try to break it. We keep trying. But we're honestly, we're just really sold on the product. It works great. It provides all kinds of benefits, and we're just going to keep using it more and more.
Well, it's important in the industry to hear it directly from a utilities experienced mouth. So we appreciate that very much, Jim Lehan. Thank you. And thank you to NV Energy for participating today. We appreciate it and look forward to watching what you do as you continue to try to break this conductor and install it in more and more applications around your service territory. So thanks again. Okay, Dave Bryant, what a great day. A couple of great clients of yours, Southern Cal Edison and NV Energy. And give us some concluding remarks, Dave Bryant, and we'll hand it off.
Thanks. Well, I think we all are very much aware of the severity of the need to electrify, reduce our carbon footprint and all that kind of stuff. So there's a lot of challenges that the guys face, but I tell you, in addition to helping develop the technology going back 20 plus years ago, my biggest takeaway is the amount of pleasure that I've had from making new friends and helping people solve their problems and being surrounded by a group of great people here at CTC and our customers. So I want to thank everybody for their interest and their time, and look forward to answering any questions offline that haven't been addressed today. So thank you.
Yeah, well, thank you, Dave, for your sponsorship of this webinar today with Energy Central. It's a great, timely webinar. A megatrend in our industry is that we do need more transmission capacity out of existing right-of-way, and here's a tool in our toolbox with advanced composite core conductors. So thanks to CTC Global for sponsoring, and PJ Davis, thank you for Energy Central in making this happen today, and we'll hand it back to you.
Thanks, Dave, and thanks, panel. This was a fantastic presentation. For our audience, look for an email from us containing a link to the replay to share with others, and take a minute to complete our survey. We'd love to hear your feedback. Makes us even better for future events. From everyone here at Energy Central, thank you for attending. This does conclude today's presentation.